All right, last time we started section 4.4, we were talking about other bases. Specifically, we're going to be looking at conversions as we finish up this section today. We looked at 4 different number bases, base 10, base 5, base 7, base 12. There's nothing super special about these 4. They can generalize. You could give me any base and we could do the same sort of an argument and write out the list of numbers and numerals that are there and add to it if we're over base 10, take away numbers if we're under base 10. We could do this for any of them. And so you're going to see others. It's not just going to be these 4 that are going to be having questions about them, okay? But they work all the same way. You actually use other number bases, and you might not be aware of it, but I want you to think for a minute. Can you think of anywhere that you see other number bases used in real life? Got a nod. Do you have one that you can think of for us?
Yeah, I was thinking of like a clock.
A clock. So tell me what you mean about a clock.
So like it only goes up to 12 and then like 24-hour time system.
Yep. So clock is a very good example, not only with the hours, but with minutes and seconds as well, right? The minutes and seconds go up in that. So the minutes and seconds component are a base 60, kind of like our Babylonian friends, right? And then we've got sort of the base 12 going on there. We do use the 11, the 10, the 12, all those as a 2-digit numeral, but it still has the same features that a base system would use with what we've been talking about. That's a really good example. There's another one that's really common that you guys use all the time. You don't even know you're using it. That's probably the problem. Okay, I would bet money that every single one of you has a phone somewhere nearby you, right? So technology. Technology is programmed in what base? Do you know? Binary, which is base 2. Base 2. So base 2 means that you only have 2 numerals. You have 0 and 1. The 0 and the 1 are on and off. So every feature is composed on and off. Also, computer programming is also done in what's called hexadecimal. Do you know what hexadecimal is? Okay, what does the word decimal mean? Decimal system is what we have. What's our base system? Base 10. So decimal means base 10, right? A decimal point, right? You've heard that before, of course. Decimal. Do you know what hex is? What's that prefix mean? Close. 6. Like a hexagon has 6 sides. So hexadecimal means it's base 16, right? A 6 and base 10, it's a base 16 system. So there is some computer programming that's done in hexadecimal. So you don't see them used, but for any of you who are interested in computers or who have a phone, which is all of you, you're using it all the time. The clock's the one that you make use of like cognizantly all the time, and you don't think anything about it as being odd. It doesn't have different numeral, like we don't have a numeral for every one of the values, but it resets the same way that we're resetting these values. So the first thing that we're going to look at is taking another base, kind of like we did with the Egyptians and the Mayans and whatever. And what we're going to look at is finding a number that comes before a value and the number that comes after it. Now, typically speaking, the questions that show up like this, one of the two is really easy, and it works just like base 10. And the other one has to make you think, okay, now that doesn't work here. What I would normally do in base 10 doesn't work for this value. So if we see this number, 1, 4, and you might notice that I keep saying it as 1, 4. I don't say it as 14, because when we say teen, we mean 10, and it's not base 10. So it's not a big deal what you guys say, but just be aware. That's why I'm saying it sounds kind of funny. It is 1, 4, base 5. Okay, 1, 4. Okay, so the one that's easy here is the number that's before 1, 4. In fact, we wrote it on the other screen. What number comes before 1, 4? 1, 3. Yep, 1, 3, base 5 comes before, so I'm going to kind of list them in order. Then we have our 1, 4, base 5. In base 10, if we were working with this number, the next number would be 15. But there's a problem with 15. What's the problem with the 15 if I were to write it down if I'm in base 5? There's no 5s in base 5, right? So when we run out of digits, right, when we run out of digits in a base, we have to increase the other value. Like when we run out of digits in base 10, like 19, I can't do, like a 1 and then a 10 in the ones place, right? I can't do that. That doesn't work. I have to increase the tens digit to the number 2. Are you with me? right? The number that comes after 19 is the number 20 because I've run out of single digits in the ones place. So when I run out of single digits in the ones place, I do the same thing no matter what base I'm in. So the number that comes after 1, 4 in base 5 would be what number? 2, 0 in base 5. So this is our next value. So these are the two values it's asking me to find, the one before, the one after. So as you're doing this inside of MyMathLab, it's going to be like that, pretty much, right? One of them is going to be really easy and you're going to be able to get it quick. The other one's going to be the one that's going to have to pause and think, wait a minute now, what system am I in? Now our second example, it's the exact opposite. So if I were to take the 14, right, my 1, 4, it was easy to just take 1 away from the 4, right? It's harder to take 1 away from here because there's a 0 in the ones place, right? So it's the one before that's going to be harder to find on this one because I have a 0 in the ones place. The one after is easy, though. So let's do that one. A0, 0, base 12 is where we are. What comes afterwards? Don't overthink it. A0, 1. Yeah. Right? If you increase 1, you just add 1 to it. This is base 12. So how do we get the number that comes before? Well, there's a couple of different ways we could do this. I would like for us to think about the way our system works. So instead of looking at A0, 0, pick another number that's an actual number that we use instead of an A. Somebody give me one. Don't everybody talk at once. 4. Thank you so much, Madison. I appreciate it. Okay, so we're going to look at the number 400. Okay, what comes before 400 in our base? 399. I'll put it above it. Okay, everybody good with that so far? So let's think about what we did to go from 400 back to 399. Well, I took my 4 and I turned it into a 3. Right? I went back 1 in the hundreds place. And then what happened to the zeros? They became 9s. In particular, they became the biggest value I have in base 10, right? 9 is the biggest value I have. So let's think about that from that perspective and look at the number A00. So if I take the A, that's the hundreds place, right, the third digit, and if I go back 1 digit, what number comes before A? 9. So the number before is a 9. Okay, that's the third digit from the right. The other 2 digits have to become the biggest value that exists in this base. So what is the biggest value that exists in base 12? 11. And how did we call 11? Like what letter or number did we use? A was 10. B was 11. So over here, right here, remember? So down here, A is the number 10. Oh, because I wrote it wrong. No wonder. It's because we were doing fast at the end of class. Everybody fix this. This should say 10 and 11. No wonder you're looking at me like I'm crazy. I'm sorry. So sorry. Oh, my goodness. Too fast at the end of class. Okay, did everybody get that fixed? Yes. Okay, now it's going to make so much more sense. I am so sorry. Okay, what's the biggest number in base 10 or 12? B. Okay, so I think the confusion that's on your face, Dylan, is because there's a number 10 right here. Yeah. Okay, so the reason there's a number 10 right here is not because this is the number 10, which is why I don't want to call it 10 either. It's because this 1 right here is in the 12s place. So I've got 112 and 0 ones. That's what this means, 112 and 0 ones. So does it look a little bit weird? Yes. But this part's correct. Okay. So the biggest digit in base 12 is a B. So these are the 2 B's here. And then I would have base 12. Okay, I want to show it to you another way, though, because you may not like that one. And I want to have another option if you don't like that one. So another way that we could have gotten 399 is we could have subtracted a 1, right? Sure, we could do it that way. So let's think about it from that perspective now. All right, so we have the number A00, and we want to subtract the number 1. Well, I can't take 1 from 0, not directly. That doesn't work. So I need to do some regrouping, yeah? Okay, so my A will get decreased by 1. The number before A is a 9. And as I do that, I need some more space. Let me shift it a little bit. As I do that, I have to borrow. But whatever base I'm in, I'm borrowing that value. Okay? So if I'm in base 12, I'm borrowing 12. Just like in your system, base 10, we borrow 10. Every time we borrow, we're borrowing 10 from the number to the left. So we borrow 12. And I know that I'm going to write a two-digit number here. We do that in our system too. We write two-digit numbers for subtraction in the middle of it all the time. That's not a problem. Now, I haven't gone far enough, though, because I need the number to be all the way to the right that I'm going to be subtracting from, right? So I need to borrow again. So I take my 12, and I borrow it again, and the 12 becomes an 11, and this 0 becomes a 12. Okay, I'm borrowing 12 in base 12. And now I'm able to subtract. So what's 12 minus 0? I'm sorry, 12 minus 1. That's 11. For the now, I'm just going to write it as an 11. I'm going to put place values in. And then I have 11 minus nothing, so this is an 11. And then I have a 9 down here. Okay, is everybody right where I got the 9 and 11 came from? So whatever base you're in, so if you were in base 13, you'd be borrowing 13. Thank you so much. If you were in base 5, what are you going to be borrowing? 5. If you're in base 7, you're going to be borrowing 7. Okay, so this is what you're borrowing within that base. Now, just like in our system, we can't have a two-digit number in these one-digit spots. So we have to, at that point, figure out what they're supposed to be in a one-digit form. And the one-digit form for the number 11 is B. And it goes up like that all the time. So A is 10, B is 11, C would be 12. You guys don't want to talk to me today? C is 12. D would be 13. E would be 14. And we could do this for all 26 letters, right? Nobody's going to make you do it for 26 letters in my math lab, okay? But you could do that conceivably for all the letters. Agreed? Yeah, we could do that. Okay, so that's where we get the B's. So in base 12, and in all the bases that are bigger than 9, right? These would be B's. So we would have the same 9 because that's a one-digit number already, and then I'd have a B and a B. So it's another way that you can get that value. All right. Where am I now? Aha. Okay. So the next thing we're going to do is we're going to actually convert between bases. So there's two ways to do conversions. We're going to take our numbers and put it in this other number form. We're going to take another number and we're going to put it back in our form. Those are the two directions we're going to go. It's exactly what we did with the Mayans and the Babylonians and the Chinese. We took one of our numbers, we wrote it in their form. We took one of their numbers and we wrote it in our form. Are you with me? So this is the same process. It's just that they're not weird symbols. That's the only difference. So in some sense, that should make it easier. But all the bases are different, which in that sense, it makes it maybe a little bit more challenging, right? We don't just have a fixed, it's always base 20, or it's always base 60. That part's different each time. Now, this is taking their number, right, the other basis number, and putting it in our form. So I'd like for you to make a note to yourself, something like this. When we go from base, you can put like a question mark here, into base 10, which is what we're doing, we're going to multiply. It's all about multiplication. Okay? We're multiplying. So we need to figure out what we're multiplying by, and we're always multiplying by powers of the base. So if we're in base 2, we're going to be multiplying by powers of 2. Down here, we're in base 16, we're going to be multiplying by powers of 16. No matter what base you're in, you're multiplying by powers of that base. So when we're looking at this number, I'm going to write it a little bigger so that I have more space to write this out. I have 4 numbers. The numbers are 1, 0, 1, and 1. And I'm in base 2, okay? So on the far right-hand side, this is 2 to the 0. And then I move over, I've got 2 to the 1, 2 squared, and 2 cubed. And their powers always work that way. You start with 0 on the far right-hand side as your power with whatever your base is, and you increase by 1 each time. All right? And we're going to be multiplying. So legitimately, we're going to be multiplying these two together, and we're going to be adding it to these two multiplied, and adding it to these two multiplied, and adding it to these two multiplied. Now, I'm going to write that out in a linear form instead of stacking it where it kind of almost looks like division right now. But I have a 1 that gets multiplied by 2 cubed. I have a 0. I'm just using it as a representation. A 0 that gets multiplied by 2 squared. A 1 that gets multiplied by 2 to the 1. And a 1 that gets multiplied by 2 to the 0. Okay, Now, clearly, if you're multiplying by 1, it doesn't really change anything. So 2 cubed, what's 2 cubed? 8. So this is really saying 1 times 8. I'm going to write this 1 out like this, but certainly you don't have to do so. What is 2 squared? 4. 2 to the first? 2. And 2 to the 0? 1. So those are the numbers they represent. If you want to do this all in one step, of course you can do that. So this gives me 8, 0, 2, and 1. And I add those together. So 8 plus 0 plus 2 plus 1. And what does that give me as a grand sum total? 11. If you want to reference this yourself, you can write down that this is base 10 next to it. That's fine. But if you don't write base 10, it's automatically understood to be base 10. Okay, so the number 11 by itself is the answer. Now let me give you some sort of picture when we get to base 16 of maybe an image of what's happening. It doesn't really work quite as well for my base 2, just because it's such a small base. But the picture works in general. So let's do the same thing with this next one. You're going to write out 4 placeholders. And you're going to write out underneath it, we're going to do the powers of 16. So this is 16 to the 0, 16 to the 1, 16 to the 2, and 16 to the 3. Everybody good so far? Okay. I don't really want to write down A, B, C, D above them. I'd rather write what A, B, C, D represent. What number is the A number representing? 10. Yeah, once we fixed it as 10. How about B? It's 11. C? And D? 13. Okay, that's the ABCD written out in their 2-digit form that we use. And again, we're going to multiply 10 by 16 cubed, 11 by 16 squared, and so on. And I'm going to write them out over here. So I have 10 times 16 cubed plus 11 times 16 squared plus 12 times 16 to the 1. Move this down. And then 13 times 16 to the 0. You can write out the powers of 16 just like I did on the previous problem with the powers of 2. I'm not going to do that this time, right? I'm just going to let my calculator do the whole thing because mine will actually support doing that. So if you take your calculator and you multiply 10 times 16 cubed, that's where you're going to go. In fact, I'm going to get mine out. I have that written in my notes. So I can do 16 cubed in my calculator and multiply by 10. And if I do that, I get a large number. I have 40,960. And if I multiply 16 squared times 11, I have 2,816. 12 times 16 is 192. And then 13 times 16 to the 0 is just 13. And if I add them all together, what do you get? 40-something thousand. 43,981 is what Emma said. That's what my notes say as well. Did everybody get that? Okay. So do use some carefulness, because a lot of what we just did relied on us keying things in a calculator correctly, and typos happen. Just look at your text messages. Do typos happen? They do in mine. Yeah, typos happen, so just be careful. Take your time and make sure that you're really being careful with what you're putting into your calculator. Okay, so when we take base whatever and we move into base 10, we're multiplying. So here's the image I want you to have in mind. Okay, we're going to take this example. We're going to pretend we have bags of, and I usually use crayons, so we're going to use crayons. So this 13 in the end is 13 individual crayons. Okay? This next one is bags of size 16. Can you imagine making bags of size 16? You have 12 bags with 16 crayons in each of them. Right, this sounds like what we're doing right now for our STEM day activities. We're making packages of things to make for they're 60 at a time. We're going to have 60 students at a time that are doing STEM Day tomorrow for the math department. So everything we do is in duplicates of 60. Okay, so we have 12 bags that have 16 crayons in each of them. We have 11 bags that have 16 squared crayons in it. So 16 squared is 256. So we have 11 bags with 256 crayons in them. Okay, so these numbers don't work perfectly for boxes of crayons, but have you seen boxes of crayons before? And they come in all these different sizes, right? That's the idea I'm sort of picturing, right? And then we have 10 bags of size 16 cubed, which is 4,096. 10 bags of 4,096 crayons in it. Okay, can you picture it? So somebody comes in with 10 of these gigantic bags of crayons, 11 of these slightly smaller but still really big bags of crayons. We have 12 of these bags of crayons here, and then we have our 13 individual crayons. And then they take all of them and they dump them out on the carpet. First you panic and you're like, oh my word, there's crayons everywhere, right? But if you were to count them all and put them back together in a way that made more sense to you, groups of 100, groups of 1,000, so forth, that's what we would have. We'd have 40,000, 3,981. That's the number of individual crayons that we would have, and that's the equivalent of what we're doing. We're taking something that's grouped in a way that's unfamiliar to us, and we're regrouping it in our base 10 system. Okay? Now we're going to go the other direction. We're going to take one of our numbers and turn it into one of these other bases. So again, I want us to write down that we're going here from base 10 now. That's our system. And we're moving into whatever other base we have. So base question mark, because it's going to change each time. And when we do this, if we multiply it on the other direction, what are we going to do for this one? Divide. We're going to divide. And this is exactly what we did with the Mayans and the Babylonians in 4.2, right? We multiplied going one direction. Right? We multiplied by powers of 60. We multiplied by this sort of modified powers of 20. And then the other way we did it, we divided with that division ladder. Yeah? We're going to see that division ladder come back up again. Okay? So this one's asking us to take 11,028 and turn it into base 4. So again, we've started with 11,028 crayons on the floor. And we're going to put them in bags. And the bags are going to be of base 4 dimensions or size. So we need to figure out how many it's going to take. Well, I've got the ones place. I've got the fours place. And then I need 4 squared and a 4 cubed. And I want to write down several of these and we'll figure out what they are and we'll figure out where we stop. I don't know if this is enough. We'll stop here for a moment. So clearly 1 is 1 and 4 is 4. What is 4 squared? 16. How about 4 cubed? Nope, you're close. It's 64. After that, I don't know them. So somebody's going to have to tell me what 4 to the 4th is. 256. So that's not anywhere near my 11,000 just yet. How about 4 to the 5th? 1,024. Still not near my, 11,000. So I need a few more. So let me shift these over a little bit. Make it a little bit smaller. That'll work. I need 4 to the 6th next. 4,096. Ooh, we're getting close. 4,096. And what happens if I do 4 to the 7th? And that 16,000 is too big. 16,000, what was it, Dylan?
16,380.
384. So I told you the 16,000 is too big. Can you tell me why?
It's over the 11,000.
Right. It's more than the 11,000 crayons we have. So there's not going to be a need for this one. I don't need that one. So just find the powers of 4, or the powers of whatever base I'm working in, until I get a number that's too big. The biggest number that I have is the one that I'm going to start with my division for. So 4,096. So remember our ladder. So this is 11,028, and I'm dividing by 4,096. And our calculator still does most of the work here, but not all of it, right? Like we do the division in the calculator, but we have to interpret what we're finding. In particular, as we do this division, we want to know how many whole numbers come out of doing this division. So how many whole times does 4,096 go into 11,028? Twice? Okay. 2 times. So So 2 times 4,098.6, sorry, what is that? 92? All right, 8,192, and we subtract. So 11,028 minus 8,192. What does that give me?
2,836.
Cool. Okay, no skips allowed. We did 4 to the 6th, which is the 4096. Now we move to 4 to the 5th, which is 1024. Okay, so even if it goes in 0 times, we have to represent it. This one, it goes in more than 0 times, but just as a reminder. So how many 1,024s are there in 2,836? 2 again. And what is 2 times 1024? 2048. And we subtract. So what is 2,836 minus 2,048? 700 something. 788, good. What will I divide by next?
4
What one?
to 4.
4 to the 4th, which is 256, right, good. Sorry, I just couldn't hear you guys. 256. So how many 256 are there in 788? 3. So not 2 this time. What's 3 times 256?
768.
768. When I subtract this, and what do I get? 20. What do I divide by next?
4 to 2.
Yeah, 4 cubed, which is 64. This is the one where people mess up, right? Because it feels sort of silly. But we need the placeholder. We learned what happens when we don't have 0 placeholders, right? We go extinct. That's what the Babylonians did, right? They went extinct. At least their number system did. It didn't work out very well for them. Okay, so it goes in 0 times. That's fine. We just put a 0 there as a placeholder. We do our subtraction and we move on to the next value that might go in. So 64, we go down to what? 16. Okay, so we did 64. Now we're doing 16. So we're going to divide by 16. It goes in
0 times. Or 20.
1 time. Yeah, so 16 will go into 21 time. 1 times 16 is 16. Subtraction, and I get 4. What will I divide by next? 4. 4 goes into 4. 1 time. And it's really tempting to say you're done here, but you're not. You're really close. Why are you not done? You still need to divide by the number 1. So we always divide by every single power, even when the number is 0. Obviously, 1 goes into 0 0 times. I have the same remainder 0 happening here. But the reality is that over here is your answer, just right there. Our answer is 2230110. And I have to write the base next to it. It's base 4. 2230110 base 4. So unlike Babylonians and Mayans and Egyptians and all of them, this is not a multiple choice question. You can write this into my math lab, right? So that's how they're going to usually show this, is they're not going to give you multiple choice options. They actually expect you to be able to write this in with the right subscript and so forth, okay? All right, another one much like this. We have 99,999, and we're going to put it into base 9, just because it's fun. Lots of 9s everywhere, why not? Okay, so there's no 9s in base 9. It doesn't work that you can't just like somehow turn them into something there, right? There's no 9s. But we need to know what the base 9 values are. So I have the 1's place, I have the 9's place, and then I have 9 squared. What's 9 squared?
81.
81. Yep, you're right. What's after 9 squared?
720.
Yep, 9 cubed is 729. Remember, I'm going to keep going until I get a number bigger than 99,999. 9 to the 4th.
6,561.
And 9 to the 5th.
59,049.
Okay, What will 9 to the 6th be?
531,441.
531431
531,441.
441. Okay. All right. I've exceeded the value I needed, right? I needed 99,000. I'm at 531,000, so I don't need this last one. You could have stopped at the 9 to the 5th if you noticed already. Hey, I'm already at 59,000. It's definitely going to get too big with the next one, so that you could have stopped a little bit earlier if you'd wanted. But these 6 values are the ones I'm going to divide by, starting with 59,049. So let's go over to our division ladder. So I have 59,049. And I'm going to divide 99,999. And it's going to only go in one time. That one's pretty quick to see. But then I need to subtract 59,049. And if I subtract, what do I get? What was it?
40,900.
49,050? Did I write it right? Is that what you guys have? No.
Yeah, switch the numbers. It's 40,900.
40,950. Okay. Sorry, I have pieces of this written down, but I don't have all of the pieces written down. Okay. What will I divide by next? 9 to the 4th, which is 6,561. Okay, how many times will 6,561 go into 40,950? Whole number times. 6 times? And what is 6 times 6561?
39,366.
Okay, so we went from 40,000 and we're subtracting a 39,000-ish. What do we get? 1584? I definitely have typos on my paper. What did I do? I don't think it's 39,366. Is that the right number? That doesn't count. It's not quite right. No, I think I wrote 3. Okay, I know what it was. 39,366. I know it's wrong. Okay, 1584. We're good. Sorry, typos everywhere. All right, what will I divide by next? 729. How many times will 729 go into 1584? Twice. So 729 times 2 is, I have 1458. And if I subtract that, what do I get? 126. Now what will I divide by? 81. How many 81s are there in 126? 1. When I subtract, what do I get? 45. Divide by 9. A lot of repetition, right? And just do the same thing over and over again. How many 9s are in 45? 5. I have a remainder of 0, but I'm not done because I still need to divide by 1. Yeah. 1 goes in 0 times. Very unexciting ending, but I do need the 0 as a placeholder, and all of my values right there make up my answer. 162150 base 9. Now let's pause for a moment and just make a comment. Let's say that we were turning this into base 13. If you were turning this into base 13, you do the same powers, 13, you do the same division and everything, but what would happen over here on some of these values on the right-hand side that are highlighted in yellow is they might be 2-digit numbers, right? You could get the number 12. You could get the number 11 or the number 10. So when you would write it over here in these terms, you'd need to make sure that you turned that 10, 11, or 12 into the A, B, or C, right? So then it becomes more like what we did with the Babylonians and the Mayans, where we actually have to turn it into a symbol because we don't have two-digit numbers when we're writing these down. We only have one-digit numbers. So A, B, C, and so forth would come into play. All right, there's a couple more things in this section that are interesting that I'd like to point out. They ask you, in some cases, to turn a number from one base into another base, and neither base is base 10. Okay? There are some shortcuts in certain cases, but I'm going to show you a general form because it will work for all of them. Is that fair? Okay? I don't want to teach you a shortcut and a general form. That seems a little bit redundant. So I'm going to show you a general form, and the basic idea is this. Whatever base we start in, this case 5, we're going to first go into base 10, and then we're going to move out of base 10, and we're going to go back into whatever base they tell us, in this case, base 7. So it's going to be a two-step process, okay? Turning from our base in the middle. Our base will be in the middle value. Now, when we move from base 5 into base 10 and base 10 into base 7, we're going to do a multiplication step and we're going to do a division step, and we need to make sure we get them in the right order. So what's the step first if we're going from 5 into 10? That one's multiplication. So I'm just going to write an M right here. You can write a multiplication symbol if you want. And if you're moving from base 10 into base 7, you're going to use division. So we're going to do a multiplication step and a division step. So this is a two-step problem. We're going to do the multiplication step first. I'll call it the M step. And we're moving from 4, 3, base 5, into base 10. So I have a 4 and a 3. It's simple compared to the ones we were doing because it's just a smaller number. These are 1s and 5s, and we would have 5 squared and 5 cubed. So this is like having 4 $5 bills and 3 1s. Can you picture it? Do any of you use cash anymore? Can you picture it? Okay, just checking. My kids don't seem to picture cash very well these days. 4 5s. Well, that's 4 times $5, right? And 3 1s. How much would that give you? 23. This is $23, or the number 23 for what we're doing. Then the division step. The division step is that we're going to be dividing by powers of 7. Well, we've got 1, we've got 7, we have 7 squared, which is 49, and that's too big because our number's 23. I don't need the 49. So I only have to divide by 1 and 7. I can do that. So divide by 7, number's 23. How many 7s are in 23? It's 23 because we have it down here.
Don't you multiply it by 1, 5, I'm done.
We already did that step. We already did the multiplication step. Right? We multiplied the 4 times the 5, and we multiplied the 3 times the 1, and we added them. So we've already done the multiplication step. Okay, we took care of that already. So you're right, we did need to multiply, and we did. 23. So how many 7s are in 23? 3. That's 21. Remainder is 2. And how many 2s are in 1? 2. So we end up with this number, which is 3, 2, base 7. And that's not like, oh my goodness, look, it went from 23 to 32. It's not like that. It just is the way it worked out. Okay, that doesn't always happen or anything like that. Okay, you ready to look at the next one? Same thing. An in-between step, so we're doing a two-step process. So we're working from base 2 into base 8. It's a really long base 2 number, isn't it? I don't know how many we have, but we're going to have to write it out long-wise. So we're going to go 2 to 10 to 8. All right, cool. So multiply and then divide, right? So we have 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. I think I wrote them all out. Okay. So this is the ones place. This one's 2. So I'd like for you to take your calculator, and we're just going to do this together. I don't want to write out powers of 2. I'd rather just write out what the number is. And we don't have to do it with powers. You can actually do it with a cyclic process. So take your 2 and multiply by 2. I know you know what that is, but just do it with me for a second. 2 times 2 would be 4. And then multiply that answer by 2. 8, and multiply that by 2. 16, and multiply that by 2. 32, and multiply that by 2. 64. Some of you are still in your head. That's good. 128, and, well, I just spoiled the fun. The next one's 128. Oh, my goodness. All right, what's after 128? 256. And then after 256? 512. And what's our last one? 1024. 1024. Yep. 1024. Okay. So that's called a geometric pattern, by the way, when you're able to multiply to get the next term, the next term, and the next term. And so you can do it that way as well as doing it as powers individually. And so we're going to add each of these together multiplied by either 0 or 1. So the ones that are multiplied by 0 right now, since we've done this a couple times, I'm just going to leave them off. And the ones that are multiplied by 1 are just themselves. So we have 1024 times 1, which is 1024. We have 512. But we don't have 256 because there's a 0 in that place. We have a 128, but we don't have a 64. We have a 32, a 16, an 8, and a 4, but we don't have a 2, and we have a 1. So these are the numbers that we're going to be adding together. So grab a calculator. I don't think, you might have done all the multiplication by 2 in your head, but I don't think you want to add all the numbers together in your head. What does that give you?
1725.
Okay, 1,725. What base are we in?
2.
We're in 10. We were in 2 and now we're in 10. I'm only mentioning it here because I don't want you to stop. We're halfway done with the problem. We're at 1725. After that, I need to turn it into base 8. So I need some powers of 8. So let's write down some powers of 8. Well, you've got the 1's place and the 8's place. 8 squared is 64. And we can do the same thing we did with our 2's. Just do 64 times 8. It's 512. Times 8. 4096. And that's too big. Why? Yeah, our number's in the 1000s, right? This number's the 4000, so I don't need this one. So the division step we're about to do is a lot quicker than the multiplication step because there's fewer values that I have to divide by than there were that I had to multiply by. So we're going to divide by 512. And we're dividing the 1725 into that. So how many 512s are there in 1725? 3's, right? 3 times 512 is,
1526.
yep, 1536. What do we get when we subtract that one?
189.
189. And we'll divide by 64. How many 64s are in 189? 2 or 3? I don't know.
2.
It's close. All right, 2. 2 times 64 is 128. I subtract and I get what?
61.
61. Divide by 8. Well, it's not going to go in 8 times, so it must be 7, right? 7 times 8 is 56. That's one that my 9-year-old still gets frustrated with. Doesn't remember. 61 minus 56. 5. All right, and we will divide by what? 1, which gives me a 5 to 0 it out at the bottom. And the solution, or the answer to what we're looking for right here, is 3275 base 8. All right. There's one more problem that we're going to do, and then I want to show you, I'm going to go back and show you one other step in a problem that we had done that I kind of glossed over, I forgot. It's not a step that I'm particularly fond of, but I can't figure out how to let my math lab not ask it because it always asks it in a 2-part question. where what I've already done is part one and this other process is part two. So I need to show you how to do it because I can't isolate the questions, unfortunately. So let me show you one more piece of information and then we'll go back to there. All right, we want to be able to take numbers in different bases and compare them, right? So this is imagination time. Imagine you had 4 bags of 7 crayons and 3 individual crayons. That's 4, 3 base 7. You had 1 bag of 4 squared, or 16 crayons. You have 3 bags of 4 crayons and 2 individual crayons, right? So that's like person number 2. And then person number 3 has A, which is 10 bags of 11 crayons, and then 2 individual crayons. And the question is, who has the most crayons, right? That's the idea. We've got to be able to figure out how many crayons they have, and the best way to do that is to put them all in the same base. The base that makes them all the base that makes the most sense to put them all into would be base 10. So we're converting 3 numbers into base 10 to see which one is the biggest, which one is the smallest, and which one's in the middle. So we're doing 3 conversion steps, but we're turning a base whatever into a base 10. So are we multiplying or are we dividing? We're multiplying. So I have 4, 3, and I'm in base 7. So this is the ones place, the sevens place. So it's 7 times 4 plus 3 times 1. What will that give me? 31. Good job. I have a 1, a 3, and a 2. I have the ones place, the fours place, and then the 4 squared, or you could put 16's place. So I need 1 times 16 plus 3 times 4 plus 2 times 1. What is it? Is it 30? Yes, I have it written down. Yep, 30. And then the last one is the A and the 2. And we remember the A is the same as the number 10. The A is in the, 11? The 11's place. And the 2 is in the 1's place. So I have 10 times 11 plus 2 times 1. What's that one? 112. Okay, so this one says order from least to greatest. Which is the least of these 3 numbers that I just found? 30. And 30 represents the number 1, 3, 2, base 4. I'm going to put a less than sign. Sometimes you'll see them put a comma, or they may have you put a comma. Which number comes next? 31, right? And 31 is the 4, 3, base 7. So I have 4, 3, base 7 next. The largest one is the one that was 112 in base 10, otherwise known as A2 in base 11. Okay, does that make sense? Okay, so what we've done right here is the crucial part of this particular lesson, but I need to show you the other thing that's going to show up in my math lab. Okay, so let's go back and figure out where it was. Problem number 3 and 4. So I'm going to shrink this to give us a little bit more space on both of them. Okay. So I mentioned as we were working through that you could find the bases by multiplying by 2 again, and 2 again, and 2 again, or 7 again, and 7 again, and 7 again, right? Like you didn't actually have to write down 7 squared, 7 cubed, 7 to the 4th. We could just multiply by 7 to get the bases. It's from that idea that this is coming. So they call this the calculator shortcut. The thing you need to be really careful with is that there's some parentheses that can cause you to make some mistakes if you're not being really careful, okay? So if you take a look at what we're doing, we're going to start with the smallest number. So the the biggest number. I said it right, wrong. The biggest number. The biggest number is the number in the furthest left placeholder, okay? So that's the 1. And we're going to take that 1 and we're going to multiply it by 2. That's fine. You can multiply by 2. In fact, we're going to be multiplying by 2 in every step, okay? And what we're going to do then is we're going to add the next number to it. Well, it's a 0. It's not very exciting, but we add the 0 to it. And then we put parentheses around all of that, and we multiply that by 2. We add the next place value to it. What's the next place value number? I think it's a 1 in the next one. All right, so let me show you where each of these are going. There's my 1. Here's my 0. Here's my 1. Okay? So we add the 1 to it. We embed parentheses around the entire thing again. And we multiply by 2. And then the very last number in the list comes as addition at the end. The reason I don't like this is because I really feel like it masks the whole point. Why did the numbers go in the way that they did? Right? Well, they did because we're multiplying by successive powers of 2. So like if you take a look at this, that first number got multiplied by a 2 here, a 2 here, and a 2 here. And what is 2 times 2 times 2? 8, or 2 cubed. And that's the place value it's in, right? It's in the 2 cubes place. So it's doing what it's supposed to do, but it's doing it in a way that I feel like looks obscure. Okay, and you have to be careful about your parentheses. So what am I telling you? Well, I'm telling you that there's going to be some problems where they're going to put this in and they're going to say they want you to write out the calculator shortcut. And this is what they're going to expect you to write out. Okay? They're going to expect you to write that out. So let's actually do the same thing for the number here, the ABCD. So this one's going to look a little weird too. The last one looked weird because it's all 1s and 0s, so it's hard to sort of keep track of where we are. This one's going to look weird because I don't want to put in A, B, C, D. I want to put in 10, 11, 12, 13. That's why this one's going to look a little weird. But we start it with the A. The A has a value of 10. And we multiply it by the base that we're in. We're in base 13, right? 16. So it's 10 times 16. And then we add the next number. It's the number B. The number B is an 11. We put everything around in parentheses and we multiply that by 16. Then we add the next value. What's after the 11? This one's a 12. That's the C. Okay, so my A comes here. My B is here. And my C went here. And then I put parentheses around everything. And I multiply by 16. And my last piece is to add the last digit, which is the D. Whoops, sorry. Get my buttons right. And D is the number what? 13. Now, if we didn't make any mistakes with parentheses, and if we didn't make any mistakes with our powers over here, right? If we do both of these processes 100% correct, they'll still give you the same number. Both of them are going to tell you 43,981. All right? They'll both give you the right answer, just from a different perspective. And my preference is this one that I taught you, because I think it shows you where all the numbers came from. And this one feels a little bit like hand waving and a little bit magic-y and a little bit hidden about where everything's going. But I can't separate it inside of my math lab. Okay? All right.